My name is Geoff Hanley. I was the Constellation Program Manager from 2005 to 2010.
My name is Geoff Beech. I'm a team lead in the Systems Analysis branch at Marshall Space Flight Center.
One has to remember that what came out of ESAS was a concept, not a design. There's a big difference. And when we put our first designs together, and I'm talking about design of the rocket and the design of the spacecraft, and we actually tested those designs using models against what we expected for the environments that they would have to fly through. We had some pretty eye-opening problems, exceedances of loads, limits, and what have you. We had a terrible noise problem generated by the wind going by the nozzles of the launch abort tower, causing huge sound waves of issues with the spacecraft. And so we had mass issues. The spacecraft mass grew. Once we came out of ESAS, we did what's called the call for improvement. We selected the Lockheed Martin company as the Orion contractor. We got them on board. We took their conceptual design that they offered in the procurement and updated it with all of the NASA in-house design work that we had been doing to get a reconciled vehicle out of that. And when we were done with that process, the vehicle exceeded the mass limits of what the rocket could lift.
Ares 1, coming out of the Exploration Systems Architecture Study, or ESAS for short, initially had a 4-segment booster and a single SSME on the upper stage, and it was a fairly robust design. Shortly after that, it was modified to be a 5-segment solid rocket motor as a booster and a single J2X engine for the upper stage. And that change, while it seemed kind of small, it actually affected the trajectory and the robustness of the design in some significant ways, and really created some performance challenges for Ares as a system. And that was coupled with Orion being overweight initially, and they actually struggled for a long time with their weights, but there was a challenge overall for closing the mission and making sure that there was sufficient propulsive capability to accommodate the payload mass. Well, mass and performance are just critical parameters, and it's like money at home, where any potential change that's coming forward basically will be resolved into performance numbers. And it's really one of those very tangible quantities that everybody cares about. It's critical to the program, along with cost and schedule. So it was really critical to get that data right and make sure that the pedigree of the data was correct, because ultimately, periodically, we would have knockdown, drag-out discussions where we would all go into a conference room for the whole day, and all the data would be presented, and all the project managers and chief engineers would be in the room, and we would go in and have intensive discussions about everything that was on the table so that we could make effective decisions on how to move forward. The change to a 5-segment booster was subtle, but it ended up being a big deal. What it did was it kind of changed us from working with a first gear and a second gear in our trajectory during ascent to really a first gear and a third gear, and it made us depend that much more on the first gear and from a trajectory standpoint. And what that did was, when the first stage, when they did some of their development tests on the 5-segment booster, which was really outside of our experience base, there were things that hit that performance. And because we depended that much more on our first gear, that ended up really hurting our rocket at the end.
So it was all very, very first cut, in 2006 and 2007. We had first cut environments. We had a first cut at a detailed design, and we were running the design through these environments, and we had these exceedances. So we had to grow the mass of the upper stage. We had to grow the mass of the spacecraft, and we set to work, as every systems engineering effort does. We set to work whittling away at those issues. We saw what the pokeouts were, and we started addressing them. Many of them we carried in the RISC system because they were integrated issues. In other words, more than one entity had to contribute to the resolution of it. So we developed the value of the RISC system was the setting out of a mitigation plan of what actions were going to be taken to mitigate this risk, and who was assigned each action. So the rocket would go off and do some wind tunnel testing. The spacecraft would go off and do some wind tunnel testing. The spacecraft would go off and look at different design changes. They would play that back to what does it mean to the rocket to have those design changes, so forth. So it was a tool to keep the team married together on the same page. Two different, we had the rocket vehicle integration folks, we had the spacecraft vehicle integration folks, and then we had the program level systems engineering team that was responsible for making sure that those integrated issues are resolved. So that was the leveraging of the RISC system in terms of the mitigation of exceedances we were seeing. You'd see the exceedance in the TPMs, but the TPMs just tell you, what exceedances you have. They don't tell you how they're going to be resolved.
On Ares 1, the performance risk initially was something that the program technical leadership was very interested in. And of course, they were balancing margins over on the payload side and also on the launch vehicle side. So we had developed a rigorous tool for tracking the current mass and performance of the Ares rocket, and also a methodology for forecasting the potential changes that were coming up. So it was kind of a crystal ball, if you will. So the risk in the risk process was given the current performance estimates of Ares 1 and the identified threats and opportunities that were showing up. There was a possibility that we would not make our performance requirements. So at the program level, the way the overall performance was managed was through a Tiger team that was led by the chief architect, Brian Muirhead. And he had people on the Orion side and on the Ares side that reported to him directly to give him the metrics for mass for Orion and performance for Ares that allowed him to ensure that he had sufficient margins to close the overall mission. From there, the Ares part was really Marshall's responsibility, and that's where I came in. I worked primarily on the mass property side and the mass control side, but also with the performance elements, the J2X, ISP and thrust, the first stage propulsion, and also things tied to the analysis and the trajectory and the way the trajectory actually worked that all affected the overall performance. The control and mitigation was initially these technical performance measures, and the technical performance measures included not just the estimated performance relative to the requirement, but it also had the threats and opportunities in the forecasting. So we developed a probabilistic approach to that, where we really brought in the lower level element managers, and we had them and their engineering teams identify and track any threat or opportunity that they foresaw in the future. And we had them score those for consequence and also likelihood. And then those aggregate threats and opportunities were analytically integrated using a statistical approach at the vehicle level, and they were able to inform the overall encumbrance on the margins that we had as a system. So we reported against this guidance from the program using technical performance measures, or TPMs for short. The TPMs in this case were really TPMs on steroids, where they had not only the current estimated performance, but also all of the potential changes, all the threats and opportunities, together on a single sheet. And it was really the correlation of the two that was ultimately the most effective way to communicate that risk, because there was such a dynamic process. The estimates were changing all the time, and they had to be directly coupled to all of the things that the technical management team had in front of them as options. So the Ares 1 performance, we were meeting our guidance from the program, so it wasn't like we were actually doing a mitigation. At that time, we were really just tracking it and using this forecasting approach. So while we did have the TPMs down at the lower levels, at the element levels, for mass and performance for the upper stage engine, for example, and similarly for the first stage, those weren't identified as risks per se on their own. However, there were some specific risks that were things that, for example, the engine needed to mitigate. They had some issues around the nozzle extension, and there were specific risks that were identified there based on a strict risk criteria. So one of the pitfalls that we recognized in the process was that it was very critical that all of the lower level element managers were cognizant of all of the things that were being discussed. There were times when we would show some data that we had gotten from a lower level engineer, for example, and we would present that at a system level meeting, and if the element project staff did not fully understand that threat or opportunity or the change, then there was a breakdown in the meeting. So we had to get very rigorous about the pedigree of the data that we got, and we had to ensure that before we could incorporate anything at the system level, that the element office had approved and signed off on all that data. For example, some of the design changes that we took on Ares 1 were the introduction of low technology readiness levels, or TRL level, on the common bulkhead, and also thrust oscillation. At the program level, while we were in pretty good shape on the space station missions, the lunar mission was more challenging. On that one, Orion was consistently over their weight bogeys, and while they didn't come back and change our requirements, it was something that the program leadership was interested in making sure that if they did have to get more performance out of Ares, then they wanted to know exactly what kind of leeway they had. So another mitigation approach we had was to identify a lot of options outside the scope of the current funded baseline to look at what kind of other options they could exercise if necessary if we were unable to make our performance requirements under the current funded baseline. A couple examples of these out-of-scope options included incorporation of larger nozzle extension on the first stage. That would have enhanced the performance by about 1,200 pounds. Another one was to discontinue the recovery and reuse of the first stage and just make that disposable. And that saved us about 1,600 pounds of performance.
I learned that the first pass through transitioning from conceptual design to a real design, okay, where you have real models of the hardware, and you're for the first time putting them through these loads and environments, and really for a launch system, it's all about meeting the loads and environments, both for the nominal launch activity, but also for the abort cases. Aborts are something, and when you mentioned commercial earlier, abort is where I would look most deeply into what a commercial provider is doing with respect to, have they approached the problem of abort, it being the system's ability to achieve a successful abort. Have they looked into that? The methodology that they've applied, does it make systems engineering sense? And have they appropriately analyzed it? But back to the lesson learned would be in terms of the integrated stack, that those early assessments are not something to get alarmed about. You're going to have exceedances because there's so much conservatism in the models at that early date. And particularly when you're integrating a diverse team for the first time, it's very hard to really appreciate who has what conservatism built into their model. And it's only through the iteration process of different design analysis cycles that you root out the uncertainties in the models, the biases, the fudge factors people have put into their calculations. And we could have been quicker in getting that on a leaner and more consistent basis across the team than we were. But that was one of those transitions we were trying to make from the conceptual phase to the design integration phase, and we were about 6 months to a year slow in doing that effectively. That's a huge transition point.
Another lesson learned is the coupling of the threats and opportunities with the current estimates. That was really critical at making sure you fully understood the state at any given time, because there were a lot of changes that were very dynamic coming at us, things being discussed kind of ad hoc. When you put those down on a single sheet of paper and you could see, given this performance and the margin associated with it, these are all the threats, and actually those would be quantified into a single number, then you could really put those two together and really see where you were as an overall system. Another lessons learned was that the overall threats and opportunity process would be applicable not just to performance, but also cost. And we would partner with different organizations for actually doing either unit cost or support cost or development cost, but any of the potential changes that came out could be scored for performance and cost. And you could really look, and technical management could see for any individual change how the two were coupled together or whether they were not. And certainly in the cases where they were not coupled, where you were positive on performance and positive on cost, then that was a no-brainer. And similarly for vice versa. If they were negative all around, then you wouldn't do that. Another thing was, from a lessons learned perspective, was we kind of moved outside of our experience base, and we had assumed that we were working inside that experience base. And when we went to a 5-segment booster, it really changed the fundamental way that the booster operated, and it brought up other issues. We had throat erosion. We had a lot of things that deteriorated the performance outside of our experience base that we knew on the shuttle RSRM.
In terms of the integrated system, it all turns on loads and environments. That is the discipline or the area of technical concern that will drive his entire schedule. the swiftness with which we could go through design analysis cycles was nearly always driven by the how swiftly we could actually do an integrated load cycle, for example. So paying attention to that, making sure that the systems engineering team has a good process in how they coordinate that, how they manage their models, how they capture loads data for the broader team to go do assessments against, and getting that rhythm going as early as possible is key. From a systems engineering perspective for the integrated stack, if you get that well honed out, everything else will kind of fall into place, in my opinion.
If you have any questions about this risk, feel free to give me a call or the Systems Analysis Branch at Marshall Space Flight Center.
I'm very open to talking about any aspect of constellation and the lessons that we had, and the team should feel more than welcome to call me at any time to visit.